A Weird Universe of Dr. De Sitter or Red Shift Without a Big Bang by Eugene Stefanovich. This time we'll be talking about cosmology. Here is the outline. First I'll tell you about the redshift of spectra of distant galaxies. The standard explanation involves expansion of the universe and the Doppler effect. In all my previous lectures, I was trying to promote the idea that physics is about unitary representations of the Poincare group. This lecture is not an exception. We'll see how Wigner's relativistic quantum mechanics can be applied to cosmology. First, I'll show how the usual Doppler effect is explained in Wigner's theory. Then we will make a guess that the true group of symmetries is not the Poincare group, but the De Sitter group. And we will repeat Wigner-like calculations for this group. We will discover the existence of a Doppler-like effect in which the color of light depends on stars' distance from the Earth. This is the most economical explanation of the cosmological redshift, and we will briefly discuss possible cosmological implications of this idea. More detailed arguments and calculations can be found in my online publication. So, what do we know about the cosmological redshift? At the top I have a spectrum produced by an atom on Earth, and below it the spectrum of the same atom located in a distant galaxy. As you see, all spectral lines shift to the red side of the spectrum. Remarkably, the wavelength shift delta lambda is proportional to the wavelength itself, so that the ratio of delta lambda to lambda is a constant that is conveniently denoted by z. Equivalently, we can say that energies of all photons emitted by the distant atom are divided by 1 plus z. Multiple observations established the so-called Hubble's law, which is the centerpiece of modern cosmology. This law says that the redshift factor z is proportional to the distance from the Earth to the light source. One way to express this law is to say that z is equal to the ratio of the distance r and the so-called Hubble distance, which is equal to 14.4 billion light years. The spectrum in the figure is shifted by about 5%, and according to Hubble's law, it could be produced by a star that is 720 million light years away from us. Actually, the Hubble law holds with remarkable accuracy up to very large distances. This picture shows the linear redshift dependence extended to about 2 billion light years. Modern cosmology explains the Hubble law by expansion of the universe. The theory is that our world is like a four-dimensional soap bubble that keeps growing in size. This stretching of the space-time increases the wavelengths of light coming to us from distant galaxies. This is the explanation of the redshift. For a more detailed description of what is going on, one has to solve Einstein's equations of general relativity. But these solutions depend on a number of assumptions and adjustable parameters. One embarrassing prediction of this approach is that our universe is composed mainly of dark matter and dark energy, and we still don't know what these things are. Even more fundamental problems arise when we decide to extrapolate the cosmic expansion to the beginning of the bubble some 14 billion years back. How was everything created from nothing in the Big Bang? Modern cosmology has no good answer. In this lecture, we would like to stick to Wigner-Dirac relativistic quantum theory. By the way, this approach avoids using the concept of a four-dimensional space-time manifold. Moreover, it strongly suggests that such a manifold is not a rigorous concept. You can find more detailed discussions of this point in my previous lectures. For all these reasons, we are not going to associate the red shift with expanding spacetime. But what other explanations exist for the red shift? The best theory is based on the Doppler effect. It is somewhat similar to the Big Bang hypothesis, but without the space-time stretching. According to this explanation, galaxies move away from each other and from us on Earth. According to Doppler, the light emitted by a receding object shifts to the red side of spectrum. If we now assume that the radial velocities of galaxies are proportional to their distances to the Earth, then we obtain the Hubble law. Just like the Big Bang hypothesis, this theory predicts creation of the universe in a primordial explosion. Now, let me remind you about Wigner's theory of unitary representations of the Poincare group. We discussed these ideas many times, so I'm going to be brief. To make calculations as simple as possible, I'll consider a one-dimensional world. In this world, we have inertial observers performing their measurements. We should be able to define a group of transformations between these observers and build a representation of this Poincare group by unitary operators in the Hilbert space of any isolated system. In our one-dimensional world, the Poincare group has a three-dimensional Lie algebra whose generators are represented by the following Hermitian operators. Space translations are generated by the operator of total linear momentum, and the corresponding unitary transformation is given by the exponent of this generator. Time translations are generated by the Hamiltonian, and boosts are generated by the total boost momentum. The parameter of boost transformation is not velocity, but so-called rapidity, which is a dimensionless quantity whose hyperbolic tangent is equal to the ratio of the boost velocity and the speed of light. The most important relationships of Wigner theory are commutators of the generators, shown here. In addition to the three generators, we'll have the observables of mass, velocity, and position. Here is a definition of the mass operator. It can be used to obtain a very convenient square root formula for the Hamiltonian. The center of mass velocity of any system is proportional to the ratio of momentum and energy. The center of mass position is given by a similar formula where instead of linear momentum we will use the boost momentum with negative sign. This symmetry between the definitions of velocity and position will play an important role later. Let us now see how Wigner's theory explains the Doppler shift of spectral lines. On the left, I showed a typical discrete energy spectrum of a bound system of particles. This could be a nucleus, an atom, or a molecule, whatever. There is a stable lowest energy ground state and many excited states with limited lifetimes. These higher energy states have probabilities to undergo radiative transitions. They drop to a lower energy level and emit a photon whose energy is equal to the energy difference between the two levels. This textbook's picture is fine, but it is a bit oversimplified. First, it applies only to a radiating system at rest. And second, it ignores the recoil. If we want a more precise description of radiation, we have to take into account that energy levels of an atom are not just fixed numbers, but functions depending on atom's momentum. Here I show two such hyperbolas, H2 for the excited state and H1 for the ground state. Let us now consider the excited state of the atom at rest. This state is represented by the point A in the diagram. After emitting a photon, the atom should end up on the lower energy hyperbola, while both momentum and energy must be conserved. Then the momentum energy transition vector, shown by the black arrow, should be opposite to the photon's momentum energy vector that is shown by the green arrow. After simple calculations, we arrive at the following formula for the photon energy H naught. Next, we repeat the same calculation, but for initial excited state B having non-zero momentum P2. For a photon emitted to the left, its energy H is equal to H naught multiplied by a velocity-dependent factor. This factor is less than unity, so we have derived the Doppler redshift formula. There is nothing new in this derivation, but I wanted to show you how Doppler effect is related to commutators in the Poincaré-Lie algebra. Here is the logic. The Hamiltonian does not commute with boosts. This means that atom's energy depends on its velocity. This in turn means that the energy of emitted photons also depends on the velocity of the atom, which shows up as the Doppler effect. Recall that in the Hubble law, the photon energy changes as a function of distance. Can we have a Doppler-like effect in the position energy domain? This doesn't seem possible in the world governed by the Poincaré symmetry, because the commutator of the Hamiltonian with space translations is zero. So the energies of atomic levels do not depend on atom's position in space. Now comes the crucial point of our discussion. Can we be sure that the commutator of total momentum and energy is exactly zero? What if this commutator is some tiny quantity that is too small to be noticed in Earth experiments? Then we might find out that energy levels do depend on atoms' position, and that photons emitted by distant galaxies have different colors. Can this idea explain the cosmological redshift? These were just speculations. Let us now turn to more specific calculations. First, Lie algebra structure demands that the commutator of P and H, if it's non-zero, must be proportional to the boost parameter K, to the boost momentum K. This means that instead of the Poincare group and algebra, we are now dealing with the de Sitter group and algebra. The parameter tau is a free parameter of our theory. What can we say about it? First, it has a physical dimensionality of time. And second, as we mentioned earlier, it has to be very large time. In what follows, we'll also need another parameter lambda, which is simply the distance covered by light during the time tau. After we specified the symmetry group and the algebra, we can simply repeat all Wigner theory calculations and elaborate their physical consequences. For example, the mass operator of the de Sitter group differs from the Poincare mass by the term shown in blue. To get to our main results, we'll use a shortcut. We'll assume that our universe is motionless. So in all calculations, we'll set the linear momentum to zero. Then we get the formula. Then the formula for the mass operator simplifies. It becomes very similar to the Poincare mass operator if the linear momentum P is replaced by the boost momentum K divided by tau. Actually, the analogy between boost transformations in the Poincare world and space translations in the de Sitter world is rather remarkable, as I am going to show you in this table. In Poincare calculations, we were interested in boost transformations, or how the Hamiltonian looked at different velocities. In the de Sitter world, we will be interested in space translations, or how the Hamiltonian looks at different distances. Here are the Poincare boost operator and the de Sitter space translation operator. Note that in the latter case, the parameter of space translation is not distance, but a dimensionless parameter alpha, so that the distance a is lambda times hyperbolic tangent of alpha. When alpha changes from minus infinity to plus infinity, the distance a is confined between minus lambda and lambda, which suggests that the de Sitter world has limited dimension. This is in full analogy with the velocity-rapidity relationship in the Poincare world. These are the operators of velocity and position that we are interested in. Recall that in the Poincare world, we had a non-trivial relativistic law of addition of velocities. In the de Sitter world, we have a similar law of addition of distances. It is consistent with our earlier conclusion that distances cannot exceed lambda. In the Poincare world, the Hamiltonian of any system is a square root function of mass and momentum. In the motionless de Sitter world, the Hamiltonian is a similar function of mass and boost momentum k. The analogy is most visible when we express the Hamiltonian as a function of velocity or position. The Hamiltonian tends to infinity when velocity approaches the speed of light, or when position approaches the edge of the word lambda. We already mentioned the linear relationship between energy and momentum of Poincare photons. According to our analogy, the energy of de Sitter photons is proportional to their boost momentum. Now we are well prepared to handle formula for the redshift effect in the de Sitter world. According to our analogy, atomic energies form a hyperbola-like functions of the boost momentum. We can skip all calculations and simply reuse our old Doppler shift result by replacing the ratio V over C with the ratio R over lambda. Then we conclude that the energy of photons emitted by a distant atom is lower than the energy of photons emitted by the atom nearby. This formula would agree with the empirical Hubble's law if the size of the universe lambda is chosen to be equal to Hubble's distance of 14.4 billion light years. So, in the de Sitter universe, you don't have to force the galaxies to run away. The redshift depends not only on velocity, but on distance as well. So the redshift is present even in a stationary universe. Moreover, it grows with the distance in accordance with observations. This means that we don't need the Big Bang to explain the redshift. Our universe can be static. And the redshift may come from intrinsic properties of the de Sitter symmetry. Another conclusion is that the size of the universe is limited. Atoms located at the edge of the universe have infinite redshifts. There is a close analogy between this observation and the infinite Doppler redshift in atoms approaching the speed of light. Maybe these ideas would allow us to explain the cosmological time dilation in analogy with the usual relativistic time dilation. However, here one must be careful because time dilation is a dynamical effect. It may behave differently depending on the form of interaction. Some details can be found in my archive publication. Thank you.